Let's get started here. Welcome all to our webinar, Amplify Your Service Mesh Without Compromising Zero Trust Security. I'm Ashraf Syed, Product Marketing Manager for Consul. I'm joined by Van Fan, Technical Product Marketing Manager for Consul, and then David Yu, who's a Product Manager for Consul on Kubernetes. Few housekeeping items here. It is recorded, and the recording will be shared with you later on. And you can also ask Q&A in the chat. Let me quickly go through the agenda for today. We will go over some of the challenges, security challenges of today. We'll discuss zero trust and how zero trust addresses those security challenges or holes that you have in your architecture. And then we'll go into how can HashiCorp Stack and Consul in specific can help you with those challenges. And then we have some exciting updates on Consul and a demo on cluster peering, which is a new addition to Consul. And then we'll leave around 15 minutes at the end for Q&A to address any of that. All right, so let's jump into today's security challenges. So let's face it, I mean, we're now living in a multi-cloud world, right? Reaping the benefits of increased agility, virtually unlimited scale, and the ability to deploy applications in a matter of clicks. The benefits to productivity are obvious, but what are the obstacles to securing multi-cloud? So not too long ago, customers wanted to own their hardware and software. They enclosed them within physical parameters where the flow of traffic between trusted and untrusted zones was regulated by firewalls and enforced by IP addresses. This is what we call static infrastructure. Today, most companies are pursuing multi-cloud strategy that requires dynamic infrastructure. Now, certain assumptions need to be reevaluated since traffic is flowing from on-prem to public clouds and everywhere in between. So identity, not IP addresses, is the means to enforcing security through constant verification and authorization. When we talk about modern infrastructure with HashiCorp, there are several key principles around zero trust security where everything is authenticated, every action is authorized, and data is always protected. So at first, we really started as a foundational element, the concept around security, identity, sorry. And so what does that mean within the scope of security and a multi-cloud environment? Let's dig into identity a bit more. In the past, legacy identity was relatively simple. Static IPs, safeguarded applications, and network traffic over trusted networks, while one login system was all users had to manage in order to access systems and resources. However, today, identity has become much more complicated as the number of clouds, tools, and resources have proliferated, making it much harder to secure applications, networks, and users. As you can see, a lot of identities have to be managed. So with HashiCorp, we simplify identity across all platforms. And so the way to look at it is we provide a unified or global identity using Vault to broker all identities across applications, networks, and users, and across many cloud services too. This approach builds a foundation to secure everything based on identity and doing so consistently across these environments. To summarize, the way to think about securing access with trusted identity is first using Vault as a global identity broker to help secure access and data across both apps, networks, and users. So with application security, it means apps can securely access other apps and databases. Vault, in this case, tightly controls access to secrets and encryption keys by authenticating against trusted sources of identity such as Active Directory, LDAP, and cloud identity platforms. Vault also enables fine-grained authorizations of which users and applications are permitted to access to secrets and keys. For example, you might have a web app, and based on identity, it has access to either database potential or cloud API key, and while all the data is secure in transit and at rest because it's all encrypted. So we can then move to network and network ensure services they can securely communicate with other services, right? For example, leveraging identity to allow web apps and services to access the database, and doing so across different clouds and environments, different runtimes like Kubernetes and VMs and the like. Let's look into console a little more here. So think of it as a services networking platform, right? You can provide consistent security across your network by connecting any service across any runtime on cloud, and then creating trusted connections while leveraging Vault for machine identity. So this is achieved in several ways. First, by using Console to provide the foundation for tracking and routing secure and more modular services, using services discovery, which operates across multiple platforms. And then second, by enabling Console to be secure service mesh, ensuring service-to-service interaction is mutually authenticated using mutual TLS, and leveraging Vault as a PKI engine. And then authorizing service-to-service interaction using what we call console intentions. These intentions, console intentions, provide explicit layer 4, layer 7 permissions based on service identity. As an example, web service can talk to database service or vice versa for others. So the other part of securing traffic is centralizing traffic, not only east-west, that means within the service mesh, but also north-south, which is provided by Console API Gateway. And then third, we have to enable networking infrastructure automation when it's used when dealing with dynamic IPs for devices such as load balancers and firewalls, and then increasing security by reducing the amount of human-driven misconfigurations and potential data leakage. And then lastly, we have Boundary, HashiCorp Boundary, which enables humans to machine access from leveraging. Machine identity with false and human identity with single sign-on gives users least privilege access to applications and more dynamic user access workflows. For example, a web developer being granted access to a web service based on knowing the identity of the web service as well as the user. So this is where the boundary comes in. To summarize our Hashi stack, right? The way to look at it is HashiCorp deliver multi-cloud security in terms of securing access and data is really through these pillars that establish human and machine identity, and then leveraging these across key workflows that are delivered by 3 of our products, which is Vault, Console, and Boundary. With that, I'll hand it over to David to go over some of the Console 1.13 updates, which strengthens some of the security things and scalability things we talked about earlier. David, go ahead.
Great. Yeah. So thanks, Usher, for that introduction there. I just will preface by saying that for 1.12, which is a prior release, we did also do a lot of things related to Vault, such as provide a Vault secrets backend for Console and Kubernetes, which simplifies the whole process of setting up Console and storing its secrets securely, and also leveraging it for PKI across the entire mesh. But here we're going to talk about the 113 release, and I'll specifically talk about a couple of different topics, and then hand it over to Van to talk about cluster peering. But specifically related to security, there is another piece in 113 that we added, a feature that we added, that enables you to configure the service mesh for transparent proxy in a secure manner. So prior to 113, we had a connect inject init container that ran across your pods when we inject, the sidecars into your mesh. And that would require an escalated privilege, specifically capnet admin, to essentially configure IP tables for you. So if you go to the next slide, sure. What we did was we actually built a CNI plugin that allows you to actually configure that outside of the container itself. And so essentially what that means is it no longer requires you to deploy your workloads with any kind of privileges that are needed to enable something like that. And so this console CNI plugin is not really meant for network traffic, but it's essentially a CNI plugin that handles the actual configuration of the IP table rules for you. So it handles it as part of the CNI spec and that whole life cycle. And so that allows us to essentially configure a transparent proxy for you securely. If you go to the next slide, one of the things we also did related to essentially handling service mesh usability is looking at how we can enable, our developers and operators when they're deploying their workloads to troubleshoot their Envoy proxies really quickly. So essentially, when you deploy, console and Kubernetes with workloads, you will see that in some cases, sidecars get injected, and the networking piece that is involved to understand, why things are not working, usually, boil down to looking at something like an Envoy config. So we can do is we can quickly inspect the Envoy config using a single command. I know it's really hard to see in this diagram, but we do have a blog post that I encourage you all to look at for 113. And you can see that essentially in there, you can look at things like the Envoy clusters, the endpoints, the listeners, and even the filters within listeners to see what's happening underneath the scenes. And our command also is able to determine whether or not what types of proxies are within your Kubernetes cluster. So if you have things like ingress gateways, API gateways, or mesh gateways, you can simply see that using a list command. And then you would basically run a proxy read command for that specific pod name to see what's going on in terms of the config. And we'll go on to the next slide to also discuss some other enhancements that we've made. And this is more related to, the story around how do we talk to services outside the mesh. And so if you're not familiar with terminating gateways is essentially an egress gateway that allows you to talk to external services that are not in the mesh itself. Now previously what happened was in order to talk to specific services that are outside the mesh, you have to register the service with a console specifically. But in the case of external services, that are exposed as APIs by public providers, registering them is actually kind of challenging with console when you're doing this at scale. So because you don't know exactly all the endpoints that are, you need to register for a specific service because it could be load balance, right? So one of the things that we did for 113 for the terminating gateway, so if you go to the next slide, is we enable the ability to actually provide what's called an allow list for a terminating gateway. Not sure if you could advance the slide, please. And what we do is we allow you to basically define inside of a config called service defaults, which is basically global default config for a specific service, what specific destinations you can talk to through a terminating gateway. And so you could basically provide external host names and IP addresses, and that will basically allow you to use those destinations as endpoints to talk to. And with the terminating gateway, you can encrypt that traffic via MTLS with his CA key and private cert as well. And so that allows you to talk securely to external services from the mesh, and we're able to do that using this solution. So these are some really good enhancements that we've built for end users. But the highlight of 113 is actually what we'll be talking about next, and I'll hand that over to Van to talk about the new enhancement we made for service mesh called cluster peering.
All right, thank you, David, for that. 1 second here, let me share my screen so we can proceed. All right, so I assume you can see my screen here. So again, thank you for that, David. Hi, everyone. My name is Van. I'm going to talk about Consul cluster peering, the beta release of it, which came out in the 1.13, the recent 1.13 release. So in a nutshell, Consul cluster peering allows you to connect multiple Consul deployments together. We call each deployment a Consul data center. So I'm going to use those terms interchangeably, but basically it allows you to connect multiple Consul data centers together. So if that sounds familiar, if you're familiar with Consul in general, we actually have a feature that does that already. It's called WAN federation. So what gives? Why do we have cluster peering now? So to properly explain the contrast and the reasoning for why we have this new capability, I figured we'll set the context and explain what WAN federation does, right? So WAN federation, similar to cluster peering, allows you to connect multiple Consul data centers together. And when you do that, you can have services between the data centers be discovered by each other. You can also have these services connect to each other. So service A of one data center can reach service D of another data center. And on top of that, you can also do cool things like service failovers. So a service fails in one data center, any other services that are dependent on that failed service can be rerouted to connect to a failover service that resides in a different data set. So all in all, WAN federation is great and it works well today. And it's in the past, what we've done is we've modeled WAN federation where it's very pretty simple to configure, to deploy, but it does have an assumption that you're configuring this using a single administrative group, meaning you may have multiple Consul data centers, but it's really a single team or group that either owns it or has access to all these different Consul data centers, and therefore they are likely managing it, right? So under a single administrative group, that works well, right? The things that are required with WAN federation in order to create the WAN federation and manage it works well with a single administrative group. And these few things boil down to the fact that you have these shared keys between all these different Consul data centers, right? So when you configure them, a lot of these keys have to be passed between them. And a single admin group would have no problem with that because they will own everything. So having the same keys, same access across all these different data centers, not a big deal. Other things involve mesh configuration. So within a WAN federation, if you want to apply a certain mesh configuration to define certain routes or define what service can talk to what other service, these mesh configs, if you apply it to one data center, it actually applies it to all of them, right? So it's a global configuration across all of them. So under a single administrative group, that's again not that big of a deal, probably because a lot of times this same admin group or admin team likely has the same requirements, right? And the same governance and same policies. So these different configs are probably not that big of a deal under that single admin group. Then lastly, when you do upgrades, again, you don't have to coordinate it with anyone else. It's just that one single team, one single group that would have to just figure out which Consul data centers to upgrade first and then sequentially go across all of them, right? So coordinated upgrades are coordinated, but not that big of a deal if you have a single admin group. The challenge becomes when organizations have now multiple different teams or development teams, development groups that deploy and own their own console data center, and they still want to connect. So when you have multiple different teams, you're no longer using a single admin group. You have multiple different admin groups, which means some of the things we talked about earlier becomes a challenge. For example, you have keys that are specific to each team, and not every team necessarily wants to share their keys across to some other team in order to federate, right? Certain mesh configurations, again, for example, if you have a service intention that allows service A to talk to service B, one team that may want to apply that config may affect another team that does not want that same config, right? So global configs are not desired across different teams. And then obviously upgrades will be more challenging when you have more teams involved, and each team has their different schedules, their different dependencies, different logistics. So upgrades can become very difficult. In addition to that, some of the other things in terms of WAN federation that's required is that all of the different console data centers within a WAN federation need to be connected to each other over the network, right? And so for some organizations that have certain policies that limit what a network can connect to, which networks can be peered to which networks, they may have certain limits. And so having everything connected to everything as a requirement is not ideal and not possible for some organizations, for some customers. With WAN Federation, it also does not support admin partitions, which is a feature to allow multi-tenancy. So not having that feature is also an issue. Then lastly, when you create a WAN Federation deployment, it is difficult to defederate and disconnect these clustered console data centers together. So again, all in all, it's worked great for a while, but there are some of these drawbacks, which is why now we have a new model for connecting console data centers together, and that's called cluster peering. So with cluster peering, there's no concept of having a primary and secondary like there was with WAN Federation. So any console data center that wants to connect to another console data center, they will be all equal peers. And when you have these cluster peers, you will actually have separate administrative boundaries as well, meaning different teams can own and manage their own console data center, and they can still connect to another team's console data center, and you won't have the same requirements, meaning you won't have to share keys. You don't have to pass keys from one team to another in order to connect, right? You don't need to worry about configurations of configurations of one team affecting configurations of another team, right? Because each mesh configuration is scoped only to that single console data center. Then lastly, upgrades are not, you don't need to have coordinated upgrades because one team can upgrade and it does not affect another team. The other team does not have to upgrade, right? So the requirements are a lot more loose in terms of these connections, and they're not as tightly coupled, but still they provide the same functionality, which means they can allow services to connect between each other. In terms of the topology is also a lot more flexible because you don't have to connect every console data center to every console data center. You just have to connect to the peer that you need to connect to, and that's it, right? And then for admin partitions, it's also supported with cluster peering, where if you are using admin partitions, you can connect partitions between different peers. And then lastly, you can very easily decouple the peers, right? So once you create a peer and you connect them, you can easily disconnect them with a single command, right? So that's a lot, this new model provides a lot more flexibility, a lot more capabilities, and it's just easier overall to manage with multiple different teams that want to do this. Okay, so let's take a quick look at the architecture. There's the control plane and the data plane. So in this diagram here, I have two data centers that are peered together. So on the control plane, that's really the connection between the servers of each data center. So they would use the control plane to establish the peered connection, to establish the relationship. So one data center would reach out to the other and say, hey, let's connect. The other data center accepts, and once they accept, their data plane will be connected to each other through the use of a mesh gateway. And so now any traffic, any data traffic between services of each respective data center can traverse the network using this using the mesh gateway, and that's essentially the data plane that connects the services between each other. Okay. So from a topology point of view, just kind of wanted to point out a few common options in terms of connecting peers. So I have 3 data centers in this case. They're separated between 2 different VNets. This could be VPCs as well, but I'm using VNets as an example. But basically, I can connect a partition of one data center to a partition of another data center. Right, pretty basic, right? I have 2 enterprise console enterprise data centers. They can have a peering connection between the 2 partitions. I can also connect partitions within the same data center using a peer connection as well, right? And then lastly, if you have an open source, a console open source data center, which in this case I'm showing you here as a data center 3, it is an open source version, and it can also use peer. It can also be peered to another console data center, right? So in this case, it's peered to an enterprise data center. The only caveat, if you are using console open source, is that the open source data center can only connect to the default namespace of its peer, right? So there you can have multiple namespaces within a single partition of each data center. But if you are using cluster peering and you want to connect it from an open source, you can only connect that open source data center to a default namespace of whichever peer it's connected to. Okay, so that's the only caveat to keep in mind when you're using open source there. Okay, so how does it work? So I'll walk through kind of the steps of setting it up here. It's pretty basic. In this example, I have 2 data centers. There's this concept of an acceptor and a dialer and an acceptor, kind of like the phone call, right? You have someone who dials and someone on the other side accepts the phone call. So the way you set it up is you first establish the acceptor. So I have, I'm using an example of Kubernetes, but this works very similarly if you're doing VMs as well, right? But if you're using Kubernetes, there's a CRD that you would apply to whichever data center you choose. It could be DC1 or DC2, right? But you choose the data center to be the acceptor. You apply this CRD, and when you run this, kubectl apply to this YAML file, it would establish this data center as the acceptor. It will also create a token. Within this token, there's a bunch of pertinent information of the acceptor, including the server IP address of the acceptor, the server name, the peer ID of the acceptor, right? So this token becomes important to establish the connection. So what do you do with this token? Well, you need to copy that token over to the other data center. So there's multiple ways of doing this. I have an example of just, if you're using Kubernetes, you just copy it from one Kubernetes cluster to another. In the real world, you may want to do out of band, right? You may want to output this token out to a YAML file, and then give it to the other team. They would apply it to their respective data center, right? In either case, all you're doing is copying that token over and storing it as a Kubernetes secret on the other side, on the other data center. So now the other data center, what they do is they deploy a dialer YAML file, right? This is another CRD that basically will establish the connection. And notice in this file, it'll reference the peering token that I just copied over. And it says, hey, this token is located in your Kubernetes secrets, right? So when you just run kubectl apply to this with this YAML file, it'll automatically, applying it will establish a peering request to the acceptor. The acceptor says, hey, I know this token. I'll accept the request. So now you've established a peering connection. So once you have that peering connection, it doesn't mean every service can see every service, right? You want to have some control over what services this DC2 wants to provide to have exposed to DC1. So that's where there's another CRD called a export service CRD. And it's not new. It's something that we came out that was introduced in a few releases ago for admin partitions. But it's basically saying, hey, I want to export, or the service B on DC2, I want to export it, or I want to make it available to be seen or consumed by my peer. And my peer in this case is DC1. So it's just stating in this file who can see what services coming from this DC2. Okay, so that you run that command, it basically allows service A to be able to reach service B, right? And similarly, if you are applying intentions, which if we're talking about zero trust, you want to set intentions or rules to not have a default deny all policy, right? Until you allow certain services to communicate. So with intentions, you can do the same thing, allowing certain services to be able to connect to other services through the use of intentions and allowing and specifying that peer in this intention as well, right? Okay, so a few things to consider with 1.13. So as I mentioned earlier, cluster peering is, this is a beta release in this 1.13. With this beta release, there are some considerations to be aware of. The GA will be in 1.14, so look out for that. But in this current beta version, there's no failover between peers as of yet, right? So that feature should be expected to come out in the 1.14 release, right? So if you are requiring, a failover type of capability, then you can continue using WAN Federation for that. Some additional things to be aware of is that if you are using WAN Federation, there's currently no migration path to this new cluster peering model, right? I mean, again, it's in beta release. We will provide some type of migration path once we have that GA version and have all the parity functionality as WAN Federation. We'll be able to provide that for you, in the future. Current runtimes that are supported include virtual or VMs and Kubernetes currently, and again, over time, we'll add other runtimes as well. And then lastly, HCP will support this in the future, but currently HCP Consul will not have this in this current beta release, right? Will not support clustering in this current beta release. Okay, so let's go over a quick demo of the things I just talked about. And basically, I have this in a repo. You can do this at your own time as well if you want to just try it yourself. So I'll provide the link to the repo afterwards. But basically, I'm just going to show you two data centers that can be peered together, and then I have two services, one dependent on the other. So we'll be able to connect this dashboard service to this counting service to be able to have that cross peer connection between these two data centers, right? And as extra credit, if you are going to go to my repo, you can also connect additional data centers. So you can perform the whole hub and spoke model if you want. I'm not going to go over that in this demo, but you can do that as an additional option to see what that looks like as well. Again, it's all in my repo. So, all right, so I'm gonna go out of this. Here's my repo. So it's provided in, we'll provide the link for you afterwards, but you can pretty much basically go over all this that I'm going to show you. So what I have now is I have two console data centers, or two AKS clusters, I should say, right? So I have two AKS clusters. It's called DC1 and DC2. Right? Each respective AKS cluster is, DC1, DC2. And I already have one console data center deployed, right? So it's called DC1, it's already deployed. What I'm going to do is deploy another data center in my other AKS cluster. So I'm just going to do, I'm actually just going to go through this list here, right? So these steps are provided, like I said. So I've already done this step of deploying the first console data center, which is what I just showed you with these pods here. Now I'm going to just basically step through this. Oops. So I'm going to deploy my second console data center, right? It's going to be deployed on my DC2 AKS cluster, right? So once that's deployed, we'll take a look at it. And in the meantime, what we'll also do is deploy my services one service on DC1 and the other service on DC2. So we'll go ahead and do that. So DC1 is I'm applying this counting service. All right, so let's take a look at the pods. So, whoops, that's DC2. So if I set context of DC1, all right, so this dashboard service has just come up. Let's also take a look at the UI. If you're not familiar with it, let's take a look at the UI of DC1. And here's the IP of DC1. Which I think I already have it here, but basically this is DC1, right? So I deployed console and I just deployed the dashboard service on one DC, right? Notice down here, there's an organization tab that says peers. So right now there's no peers at all, right? The DC2 is still being deployed. And I can add that peering connection from here, from the UI, or I can just do it from the command line, which I'll show you shortly. So let's take a look at my pods on DC2. All right, so it's up and running now. So basically I have pretty much an empty DC2 deployment. So if I go back now here, I should now, let's go ahead and add the service of DC2. Or apply a service called the counting app of DC2. All right, so that's going to apply. All right, so basically what I'm showing here is that I have this service on the front end and this service on the back end, right? And what we'll do next is establish this peer connection. So to do that, let's go down here. The next step is to create this acceptor or apply this acceptor file, like I mentioned earlier. So I'm going to run this. This will create a console token, or a peering token, I should say. So let's take a look here. Get secrets. So you see here it's called peering token that was just created, right? So that token was just created on DC1. What we'll do is copy it over to DC2. All right, so now if you look back at this, at the UI, you'll notice that it's pending. It created a token, it's showing as pending now. So on DC2, we've copied the token already to DC2. We just have to run the next command, which is the dialer, right? So the dialer will say, hey, apply this CRD and use the peering token. So if I run this on, again, I'm setting it to DC2 to be the dialer. So the peering dialer was created, right? So if I go back to the UI, you'll notice now it's active, right? So now we've established the cluster peering relationship between them by just generating the acceptor and generating the dialer. All right. So once we have the relationship, all we need to do is pretty much export one service to the other. So real quick, if I go and look at my front end service. So my front end service, again, it's this this dashboard, right? This dashboard service. So let's put it up here. All right, so this dashboard service is showing that it's not able to connect to its upstream counting service, right? That's the connection we want to establish. So what we'll do is, even though there's a peering connection, we also need to export the upstream, the counting service to the dashboard service. So if we go down here, we will next want to export. There's a command here that's basically applying the export service YAML file. So we'll just run that. So now you're exporting it. You're on DC2. You're running this export service YAML on DC2. And once that happens, we'll refresh this, a few seconds to refresh this. Hopefully I've followed the instruction. Oh, there we go. So now there's a connection because the dashboard service can now connect to the counting service between the data centers. And so the counting service, all it's doing is incrementing a counter, and the dashboard service is showing that, right, as a very simple example of an application here. So once again, you can go through all this yourself. I provide this, the steps with screenshots, so hopefully it's easy enough for you to deploy. I've used AKS, but this works on any Kubernetes cluster as well. And you can also, as I mentioned, you can connect multiple console clusters together and have a hub and spoke model. And in terms of deleting it, all you're doing is just I say it's pretty easy to delete because you're just basically removing that dialer YAML file. So I run this and it's deleted, and the counting service should be able to connect to the upstream, or the dashboard service should be able to connect to the upstream, right? So pretty straightforward, very easy to set up, very easy to break down as well. With that, I think I will pass it back to Usher, I believe, or I guess I can just keep it here and go into slideshow mode, and Usher can recap.
Yeah, thanks, Wayne. I mean, that was a wonderful demo and shows scalability of Consul, right? And that's one of the points here, that Consul helps you reduce that operational complexity. You can run efficiently at scale while securely integrating service mesh into your application workflows. And the first thing we talked about here was service identity is one thing you need to remember for that zero trust security, to have that consistent security model. And HashiCorp Stack provides that with Vault, Consul, and Boundary, and then implementing it to achieve your zero trust security posture. When if you could move to next. So these are some of the resources that David and Van talked about. There's a 1.13 release blog. Console docs are available for you. We'll share these links afterwards. And there are a couple of really good videos from HashiCorp EU, which talks about this mesh federation and cluster pairing in specific. And then we also have that GitHub repo that Ben was showing earlier. And if you want to go and research more on zero trust, there's a white paper available. And then if you're running Kubernetes environment on Consul and Kubernetes, there's a really good site at the end where you can consult for the use cases and resources and tutorials. With that, we'll open up for Q&A if there are any questions. We'll give 30 more seconds. You can also reach out to us later on through on Console 1.13 blog. There's a link that you can see at the end. If no questions, so we'll end here. We thank you for your time. And hopefully you learned something about zero trust and Consul in specific. We'll see you again sometime. Thank you.